Hey guys, so we are going to basically talk a little bit about how your eye works now. We've been focusing on the different parts and what's composed of the eye itself, but let's talk about how the eye works. And the big way in how the eye works is through responding to what's known as visible light. This right here is what's known as the electromagnetic spectrum. And these are all the different wavelengths of energy that we have. Over here, the wavelength of energy is 10 to the negative fifth nanometers. Over here, it's 10 to the 3 meters. And what this means is when we're talking about wavelength, we're talking about light being made up, or these different energies being made up of waves. And we look at the distance between the waves itself. This wave to the middle of that wave, right? And so that's what's known as a wavelength. So these right over here, this guy has very, very short wavelengths. This one's small. Over here, this one is large. Now their size is inverse to the amount of energy they have. This guy has a lot of energy, high energy. And this over here is the least or the lowest form of energy. So they are opposite. And you've heard of these gamma rays, X-rays, UV, infrared, microwaves, and radio waves. Now, the small area in the middle is the only one that our eye is concerned with. It's the only one that eye can pick up. And this is what's known as visible light. And it's between 400 to 700 nanometers. Now, as you can see, we had photoreceptors in our eye that picked up light. We had two kinds. We had cones and rods. Which one was responsible for picking up or being able to detect color? You would be right, cones. And if you notice here, you have different cones, or those different cells that will pick up different wavelengths of light. So you have here where you're looking at the blue cones, which are 420. You have cones here for 500, 300, and 560, 530. So if you have these cones, you're going to pick up these colors. Now, if you don't have the cones, you won't pick up these colors. Thus, when we talked about color blindness, you wouldn't have these cones, so you wouldn't be able to pick up those colors and tell the brain. Now, light basically comes in from the outside, right? And when light comes from the sun and hits something, you're either going to see colors, like red, blue, green, yellow, or you'll see things like white or black. White is basically all colors put together. So if I have a white shirt on, essentially, you see white because as the sun, the light rays or energy is coming from the sun and it hits my shirt, it's not going to absorb any of the colors. It's all going to bounce back and it's going to go into your eye. And so that's why you see white. And that's also why in the summer you like to wear white, because it's cooler, because you're not absorbing the energy or light energy. Now, black means that your eye is getting none of the colors. Whatever you're looking at is absorbing it all. So essentially, if I have a black shirt on, the light energy from the sun comes down, and because of the dye molecules that are there, it's going to absorb, those molecules are going to absorb all the light energy. And then basically nothing gets bounced to your eyes. So what you're seeing is an absence of any energy there. That's why if you want to be warmer, you can wear black in the winter and it's going to absorb at least that sun that's coming, if it's a sunny day, from the sun. Now, as we're seeing, as light is coming in, there's this process of refraction that's going to change that path of light as it enters. So refraction is basically defined as bending of light rays. And this can happen due to the change of speed of the light as it's passing. So the best way that I can talk about this is if you're on a beach and you're running this way through the air, you can run pretty fast. But what happens once you hit the water? You'll slow down. Why is this the case? You slow down because you're passing into a new medium. And that new medium, water, its molecules are closer together. So there's less room for you to move through them. Where air, it's a gas, right? Not a liquid. And so the molecules are farther apart. You get less resistance against pushing through them. So you can go much faster. Light behaves the same way. As it's going through one medium, right? And so if we have, say, glass here, and you have air here, this air doesn't have a lot of molecules that the light energy can't pass. But once it moves and goes into glass, it's going to slow down just like we do and change directions, right? Just like we do when we hit the ocean. So, anytime we enter it at an oblique angle, this will happen. So curved lenses, which is what we see in the eye and even on the cornea, right, is going to refract light. Light that's refracted essentially creates inverted images. So with this being said, guys, what in the eyeball is curved and refracts light? I've already mentioned one, right? The main that we're going to talk about is the lens. Another thing that can help refract light is the cornea. So let's have one of our good friends here explain how refraction works.
Bill Nye the Science Guy. Bill Nye the Science Guy. Bill Nye the Science Guy. This magnifying glass is making my eye look big. Now, why is that? I don't know. Please consider the following. Okay. When light enters something like air, water, glass, or plastic, it slows down a little. And when it slows down, it changes direction. See how one eye is lower than the other? See? Take a look at this. Here are 3 straight beams of light. When they go into the piece of plastic straight, they come out straight. But if the plastic is tilted, the beams of light get tilted. See, they change direction, so they come out this side offset. Now, what would happen if the piece of plastic didn't have straight sides, but had a curved side, like a magnifying glass? Well, the light would change direction, right? Because the surface of the plastic is curved, each beam of light enters the piece of plastic at a slightly different angle, and it changes direction a slightly different amount. Look, Over here, the beams of light come together at a single point. This is called the focal point. Now, what about the magnifying glass? Well, suppose your eye were over here, and light from the room were bouncing off of your eye and going through the piece of plastic this way. Well, then, the small area at this end would be spread out over a large area on this side. Your eye would be magnified. Thanks for joining me on Consider the Following.
So these are kind of showing how you can focus light by a convex lens. So in this example, you can see that we have a convex lens right here. And so if you have this point source here, essentially, depending on what angle it comes in and what part of the lens it comes, it'll actually focus all of that in one point on the back. So basically what we're doing here when we have our lens, it's showing you here focusing of 2 points of light. So once we get into our lens, right, we're going to be focusing on quite a few different points here. But if you noticed that as this comes through here, it refracts, and then we end up over here, right? Down here, this refracts and ends up right here. So it continues on its path, and that's why it essentially comes and ends up in the opposite side. And so the image that our lens makes is essentially inverted, which is upside down and reversed. Now, what's really interesting about this is we try to understand, or we researchers in the past have tried to understand, are we born with the capability of our brain flipping things right side up, or are we born seeing everything upside down, and then over time our brain learns? And right now the consensus is that you're born seeing everything upside down. That's why children have such a hard time with depth perception, or not children, but babies, right? Trying to figure out where to touch and grab, and they just seem like they don't really have very good perception. And it's because they believe that when they're born, they see everything upside down. And in time, our brains adjust to being able to invert the image so that you can walk normal and interact with things normally. So when we go on a path from when the light comes into our eye through when we see it, it actually has a very specific pathway that happens. And so light is going to enter the eye. It's going to go through the cornea. That's one place it's going to refract, right? It's going to go through the aqueous humor, and then it refracts as it goes into the lens and as it exits. Then it goes through the vitreous humor, the entire neural layer of the retina, and then it finally gets to the photoreceptors. So light essentially refracts in 3 places along this path. The majority of the refractory power, when you're just looking normally, is in the cornea. And basically, we get the change in the lens curvature when we're trying to focus on things close up, like that fine focus. And so the main power is, refractory power is the cornea during normal vision, because the lens is not really changing. So let's review a little bit about the eye, and then we'll talk about the focusing for distant vision and close vision.
Sight, a precious gift we can't take for granted. Our eyes are windows to the wonders of the world. All we know and love, experience and discover, ponder and cherish. Let's peer into the workings of the eye, a unique and self-sustaining system. The reflected light of the world enters through the crystal transparency of the cornea, aqueous humor, lens, and vitreous humor to project onto the photoreceptors of the retina, whose impulses converge on the optic nerve, and then to the brain, to be transfigured into imagery and imbued with meaning. Continual adjustments to the pupil and lens regulate the entry and focusing of light. In today's world, the eye's surface is constantly challenged to protect itself and adjust to changing conditions. Every blink helps our eye's natural defense system, the tear film, retain moisture and maintain visual acuity. Tears contain potent natural disinfectants to keep bacteria at bay. And the tear system washes away impurities to maintain eye health. The miraculous biology of our eyes inspires us to develop ways we can protect and maintain comfort for these remarkable structures. For all the wonders our eyes provide throughout our lives, we owe them our attention and ongoing care.
So let's talk about how our eye focuses for distance vision. Our eyes are actually best adapted for distant vision. So, and that far point of vision is basically at 20 feet. And so this is the point where, or the distance, beyond which no change in the lens shape is needed for focusing. So think about it. Whenever we need the lens to change shape, it's so that we can see things that are really close. And that is something that is, evolutionarily speaking, hasn't always been something that has been really important. At one time, it wasn't important if you could read a book. At one time, it wasn't important if you could do needlepoint, or if you could write on the computer, or any of those things. It wasn't important. What was important is if you could see food from a distance, or you can see if there was a threat coming at you, like a bear. And so 20 feet or 6 meters was the optimal distance that your body basically adapted to see. So that's why when you're basically reading something and your eyes get tired, you just kind of look off at a distance, because that is a point for which the muscles in your eye that changes the shape of your lens don't have to do any work. So basically, the ciliary muscles relax, the lens is stretched flat by tension in those ciliary ligaments, and you can see fine. Now, let's actually take a look at what this looks like. So here you have our nice R. That's what we're looking at. And this is far away, 20 meters or so. And so if you look here, you have the light entering. Of course, it refracts at the cornea, refracts again here and here, right? And then it goes to the back of the eye where the retina is. Now you have this other side that's at the bottom of the R, right, come here. It's going to refract here, here, and here. And as it moves, it's going to hit the back. So that it should explain why you see the bottom here, here, and you see the top here, here. So those images at this distance, you can see the ciliary muscles here are relaxed. These ligaments here are just stretched, and so the lens is flat. And that is going to make this image fall perfect on the back of the retina, and you can see it. So when we go to measure how we can see, or how well we can see, or when you go to the eye doctor, right? If you go in there, they're like, well, you have 20/20 vision, which means you have perfect vision, right? What does that really mean, though? What do you think it means? Basically, it says you're seeing at 20 feet what a normal person, or what we consider to be the emmetropic eye, right? Normal, what a normal person sees at 20 feet. And what a normal person sees at 20 feet is that you're able to see that print at 20 feet away without changing the shape of the lens. Right? Now, what if we have 20/40? Is that good or bad compared to bad being not as good as normal vision? This would be bad, right? This says you're seeing at 20 feet what normal people see at 40 feet, right? So your vision is half as well, or as good, right? So that means you're going to need glasses. Anybody ever had anybody diagnosed with 2200? And do you know what this is? Of course it's right. You see at 20 feet what other people see at 200 feet. That should tell you that's pretty bad, and this is what's considered legally blind. Now, what if I said 2015? What would you think about that? Good or bad? This is good, right? So this is basically saying what someone else sees at 20 feet, the normal person, that you can see that at 15 feet, right? So, let me flip. Let me actually flip this around so you can get it better. What you can see at, basically, you are seeing better than a normal person. What they would see at 15 feet, you can see at 20. Sorry, I said that wrong the first time. So that means that you have better eyesight than the normal person at 20/20. And so now let's talk about close vision. So this is for stuff that's less than 6 meters or 20 feet, right? So light that's from closer objects diverges more as it approaches the eye. So this is going to require our eye to make active adjustments. And they're going to do this through 3 processes. They're going to do what's called accommodation. And basically, accommodation is going to be the way that we can increase the refractory power. More refraction, right? Constriction of the pupil. This is going to reduce the size of the pupil. That's going to decrease the amount of light. If you remember from the microscope, sometimes having less light is better. You can see more contrast or details. And then convergence of the eyeball. We're going to get, basically, the muscles going to activate so that you can use both of your eyes to see things. And so as you can see, this is your R here. And as you come out, you can see it's so close, basically the light is going out or it's diverging from it, right? So it's gonna refract here the first time at the cornea, and then once it hits this lens, it's gonna refract here. So you can see it's actually changing directions pretty quickly. And then as it continues on, it's going to be at the bottom. Again, that's going to happen. You hit this, you get refraction here, again here, and here, and it's going to flip across. So in order for that lens to actually do the right amount of refraction, these muscles, this ciliary muscle must contract. And you can see when they contract, the ciliary ligaments that are here loosen. And so the lens becomes thicker. And that's going to help to essentially refract that light into the right area so that it can rest perfect on the back of the retina. So this shows us, this kind of shows us here, again, the accommodation. Oops, sorry guys. Right? This is the change in the lens. So that's going to increase the refraction power. Now, what is really terrible, right? That our lenses lose its ability to accommodate after the age of 50. That's the reason why a lot of times after 50 you'll start seeing more and more people wear glasses. It's called presbyopia. Presbyopia, right? And that's the loss of accommodation after or over the age of 50. And so we have what's called a near point of vision. And basically, this is the closest point each eye can focus. So essentially, that changes as you get older because you can't see as well because your lens can't change shape to refract light the way that it needs to get that image on the back of your retina. Now the constriction, here you're going to actually have the pupillary reflex that helps it to constrict the pupil to reduce light. This is going to help prevent most of the divergent light or that light that's entering at an angle too far away, right, from entering eye. If there's too much extra light in there that's not being focused on the retina, it's going to lead to blurry vision. So if we can get rid of that kind of light that's moving out or won't actually help or cannot be basically focused on the back of the retina, then we want to get rid of it. And then you have the convergence of the eyeballs, and that's basically just a medial rotation of the eyeball, right, towards the object being viewed. So both eyes kind of focus on it. So that kind of explains how our eyes work to focus. Now, we can have problems with refraction. Myopia, basically, this is nearsightedness, right? You can only see close up. So the focal point is in front of the retina. So, and we're going to look at this. The eyeball is way too long, so we end up having to make concave lenses to fix this. Hyperopia is farsightedness, which means you can see far away. The focal point is, or having you can see far away, right? So you can't see close up. Or the other one, you can only see close up and you can't see far away, right? So here, the focal point is behind the retina, so the eyeball's too short. And so in this case, you have to make convex lens. This stigmatism means you have unequal curvature in different parts of the cornea or lens. And so you end up having to correct this with basically a cylindrical grounded lens or laser procedures. So this is what it should like in an emmetropic eye or normal. Light comes in, your lens, again, is just flat, and everything goes in this focal point here on the back of the retina. And we want it to be a point so that there's not conflicting, basically, information coming into different photoreceptors. So here, if you myopic, which if you remember, this is nearsightedness. So in this, you can see close up, right? But not so good far away. So what happens here is, this is far away, it's coming in, right? It refracts, and it refracts here. So do you see how it's scattered in the back? That's why it's the scattering makes everything blurry. So in this case, if you had to wear glasses at a young age, it's because your eye is too long. Okay? And so essentially what you need to do is you have to have a concave lens. And you see this side right here, because it caves in, it's going to essentially help them move the focal point back so that it can rest on the retina in that one spot, and then you can see. So it brings in lights and it kind of diverges it out a little bit so that when you're getting the refraction, it'll help push that focal point back. So hyperopia is basically, if you have this problem, right, you can see far away, but not up close. So if you have this, basically what happened with your genes is your eyeballs are too short. When you come in, basically you have this 20 feet away, and then you see the refraction, and basically it's going to refract it to the focal point is behind your eyeball. So do you see how all these lines are coming in right here? Again, blurry because you're getting too much information and activating too many photoreceptors, not all in that same location. So what you're going to need here is a convex that brings those rays in a little bit before it hits the cornea, and then it refracts to get this focal point. So having the convex brings the focal point in so that you can see it.
You may have heard the saying that the eye is a window to the soul. Well, as ophthalmologists, we believe that the eye is a window to the body. It's a window to what we call systemic disorders, like diabetes or high blood pressure. And we can see signs of these when we look at the eye. When you study heart disease, for example, you'll listen to the heart, but with the eye, you actually look at it with a microscope. You can actually see brain tissue, which is the retina, and you can see blood vessels. And if you look carefully, you can actually even see red blood cells as they zip through the capillaries. Over 1/3 of all known genetic syndromes involve the eye. We can see signs of nutritional deficits, nerve damage in the back of the eye, and vitamin B complex deficiencies. Stress is another big one, and it can cause the cells behind the eye to start leaking fluid. It's like having a blister in the retina. And you can see it here, this yellowed area. Here we're looking at the normal retina through our slit lamp biomicroscope. You can see the orangish color of the retina. You can see the blood vessels that course over the retina. You can also see the nerve that connects the back of the eye to the brain. This patient has a really interesting finding in the iris. We call these posterior synechia. These little brown spots are adhesions between the iris and the lens. They're signs of inflammation, which can often indicate inflammation that's occurring or occurred in the body itself. In this patient, we have a little microscopic spot of blood on the white part of the eye. This little spot of blood is indicative of one of several different things. 6 out of 10 times it's caused by high blood pressure. This patient is a diabetic, and he has these small blood vessel changes in his retina. And so when we find this, we know that this patient needs to take extra care to control his or her health. So these indicators can often be seen in the eye before they can be seen anywhere else. Really, the eye is such an important window to our bodies and our health.
Sorry, guys. So that was kind of a way that people, physicians, can use the eye to help determine health. So we are now officially finished with the part of sight in relationship to sensory, right? Now what we're going to go into is sound. And basically sound are pressure disturbances. And these are alternating areas of high and low pressure. And they're produced by vibrating objects. So basically sound waves, they all move outward in all directions, and they originate from wherever the initial basically pressure happens. And it's basically illustrated as an S wave. Let's see. And something is gone here, is an S wave or sine wave. And so sound is important because this helps with one of our ear functions. I don't know what happened. I have one of my PowerPoint slides is missing. So you'll have this where it says ears perform the following functions. And so it's the sense of hearing, and that's the interpretation of our sounds that we make. And then a sense of balance, which is vestibular senses, which is both, when we're talking about static and dynamic equilibrium, is the idea of staying still or moving. And so sound waves work this way. And what they mean by a sound function, so here you have this tuning fork, and then you take this and you hit it against it. Well, this metal is going to go back, and then it's going to push forward. And when it does, there are all these molecules that are there, right? Air molecules. And so basically, it moves back, and then it hits forward. And when it hits forward, it's going to essentially compress that, compress the molecules there, right? And so you can see the sine wave goes up and down. It's showing you basically the air pressure and that distance amplitude. What you're going through there is they're showing you the different waves. So at the peak of that red line, you'll notice that's the peak of the high pressure. And that's where all those compressed molecules are together that we basically hit. And then where it goes down in that valley, you'll notice you have lower numbers of air molecules, because that's when the vibration of the fork, went back, and so they weren't pushing on those molecules to come forward. Now that is going to, those compressed molecules are going to float through to the air, and basically they float into your ear, and when those molecules hit your eardrum, when you get all those, like those sequences of all those compressed molecules together, that's going to vibrate, hit it, making it vibrate, and then you get that area where there's not, and so it goes back and forth. But that's going to be what gets your ear is going to pick up that action that's there. So we have a different thing that we want to talk about right here. Go on to the next.
Transmission of sound. Every sound is produced by a vibration. Vibration is the back and forth movement of an object. As you speak, vibrations are produced by the vocal cords in the throat. You can hear only when the sound energy reaches your ears. But how does sound energy travel? Wonder how that works? Come, let's go across to Dr. Zook. Sound energy travels in the form of sound waves.
Wait, was that it? Like, what happened? Sorry about that. Seems like something happened where it didn't work.
Movement of sound energy travels in the form of sound waves.
Yep. Well, it looks like my video isn't working, guys. Sorry about that. I don't want to restart this whole video again. So, it happens sometimes. So how do sound waves work? Well, as we were discussing earlier, you have compressions of molecules. So these areas that are high here, right, that's going to be where the molecules are very close combined, and they've been basically knocked by whatever is making the sound, right? So that tuning fork came back, and then when it came forward, it basically hit those molecules. And so those are the areas where it hits, and when it went back, this is the area that has less of those molecules. Now, as you can see, there's a difference between high frequency and short wavelengths, which have high pitches, and low frequency or long wavelengths, which have low pitches. So if you look at this guy right here, this is the one that basically is low frequency, right? So you can see there's less of them here in between, right? The wavelengths themselves, which is here, is longer. And essentially that is what determines pitch. And so we have the frequency, and what frequency is just the number of sound waves that pass a given point. Now, something that is pure tone, right? That just means they have these repeated troughs here and crests here that basically they're just repeating. So if it's a pure tone, it's one tone. These are going to be completely equal and constant. If they're not, then it could be several, right? Now, if you look here, this one, the wavelengths between the two are much shorter. So that's what's high frequency, right? You have more of these wavelengths passing to a certain point, and the wavelengths are much shorter. That's what gives us our pitch, right? So frequency is perceived as pitch. Now, how loud or soft something is amplitude. Now, with pitch, the normal range for us is 20 to 20,000 hertz. Right? Again, higher frequency, higher pitch. So these are the pitches that generally we can hear. And we'll do a test in class to see if you can hear some of those. Now, amplitude is how loud or soft something is, right? And so it's the height of the crest. So this guy right here, not very high, right? So this is soft. And how high the crest is will determine if it's really high, it's loud, right? So the height of the crest is the amplitude, and that is perceived as loudness. Okay. The normal range here is 0 to 120 decibels. If you have prolonged hearing of above 90 decibels, this can cause severe hearing loss. Just to let you know, an amplified rock concert is normally about 120 decibels or more.
Ears are constantly active. They pick up sound waves and change them into information that the brain can interpret, such as music or speech. Sound is a pressure wave that can vibrate either quickly or slowly. Slow vibrations produce deep sounds, while quick vibrations produce high-pitched sounds. Sound enters the ear and is directed through the ear canal, where it first reaches the eardrum. As the eardrum begins to vibrate, it sets the ossicular chain in motion. The ossicular chain consists of the hammer, anvil, and the stirrup. Sound vibrations move along the ossicular chain and into the inner ear. Within the inner ear, the cochlea plays a central role. It is here that the mechanical energy of sound is converted into complex electrical signals, which are then passed on to the brain. In simplified terms, the cochlea is a spiral-shaped tube filled with fluid. Sensory cells, also called hair cells, line the entire length of the cochlea. These hair cells have varying degrees of sensitivity for the detection of different tones or frequencies. This allows the ear to perceive the entire spectrum of sound. The change from mechanical vibration to electrical pulse is a complex process resulting from the movement of hair cells in the cochlea. Along the entire length of the cochlea, the hair cells are arranged like the keys of a piano. Hair cells located at the base or lower region of the cochlea are responsible for high frequency, while hair cells at the apex are responsible for the low frequencies.
So let's talk a little bit about hearing. And then we're going to be done with this part of the lecture, and then I'll start again with part 2 of this, and the part 2 will start with hearing. So essentially what we start with here is the sound is going to enter. So sound comes in here, right? So the first thing is the sound waves enter what's known as the external acoustic or auditory meatus. Right? And so those wavelengths are going to come in and they're going to hit here, which is known as the tympanic membrane, right? So the next thing we have, once it enters here, or you can even, let's actually keep that as number one. Once the sound enters here, right, it's going to hit the tympanic membrane. From there, basically this is going to make this vibrate. That vibration is basically transmitted through these guys, which are the auditory ossicles. These are the smallest bones. So we have the one that's attached to the tympanic membrane is a malleus. Then this one right here, it goes right here, and then this is the next one. So it starts right here and goes right there. That's the incus. And the last one is right here, which is the stapes. So it goes through those three guys. What happens then, this is going to bring that information, right? That's to the auditory ossicles vibrate, pressure is amplified here. So these guys are so small, what it's doing is taking the information here at the tympanic membrane, and through being able to vibrate on these, it's the way that they're put together is going to make the vibration that happens over here on the vestibule greater. So vibration is transmitted through the auditory ossicles to the vestibule. From here, that vibration or information is going to enter into here, right? And so basically, what's here is fluid, is inside here. And what that fluid is known as is endolymph. And so that fluid is located in this area known as the scala vestibuli. And what that's going to do is it's going to travel through here. Uh-oh, what did I just do? Right? And basically it's going to travel to the cochlea. Now in here, if you remember seeing the video, depending on the frequency, right? Different receptor cells, or those inner hairs on the basilar membrane within the cochlea, it's known as the organ of Corti. That's deep in the cochlea, right? Will be activated, and then from there you're going to get an uptake of calcium. The vesicles at the base of the receptor here will release neurotransmitter, which will then stimulate sensory neurons along the cochlear branch of this whole area known as the vestibulocochlear nerve. And then the auditory cortex of the temporal lobe within the brain helps interpret the signals. So let's go through this. So basically you get vibrations come in through the auditory meatus. It vibrates the tympanic membrane. That's connected here to the auditory ossicles, which are the malleus, incus, and stapes. So the vibrations enter here and they get essentially amplified. And so the stapes right here is connected or placed on this oval window. So basically the stapes is going to be vibrating back and forth and pushing on the oval window. And that pushing is going to basically push or move the fluid in the scala vestibuli. And so you can see it enters in here. And so if it doesn't have enough, if the sound is below hearing frequency, it's going to travel through the helicotrema, which you can see that area right here, right? It's deep and it doesn't excite any hair cells. But if the sound is in the hearing range, in here it's showing it's going to go through the cochlear duct, vibrate those basilar membrane, essentially, where the different hair receptors are, right? That's within the organ of Corti. And it'll activate and allow neurotransmitters to be released once calcium is taken up. And then that's going to lead to the process of being able to hear.
The ear has three parts: the outer ear, or auricle, the middle ear, and the inner ear. The auricle, the visible part of the ear, collects sound waves and directs them to the auditory canal. The auditory, or ear canal, is lined with cilia and ceruminous glands. The earwax from the ceruminous gland and the cilia protect the ear from entry by foreign matter. The thin tympanic membrane separates the outer ear from the middle ear. Sound waves cause it to vibrate. The three tiny bones of the middle ear are the hammer, or malleus, anvil, or incus, and stapes, or stirrup. These bones pick up the vibrations from the tympanic membrane and transmit them to the inner ear. The eustachian tube of the middle ear opens into the pharynx and permits air pressure to equalize between the ear and the outside air. The inner ear is maze-like, consisting of bony and membranous structures surrounded by fluid. Semicircular canals are fluid-filled bony loops that help maintain our body's balance. The cochlea is a fluid-filled, snail-shaped structure that houses the organ of Corti, the true organ of hearing. The fluid aids in the transmission of the vibrations. The organ of Corti changes the vibrations into nerve impulses that are picked up by the auditory nerve. Sound waves are collected by the auricle, or outer ear, and sent to the auditory canal, tympanic membrane, ear bones, and then to the cochlea, where the vibrations are changed by the organ of Corti to nerve impulses and transmitted by the auditory or cochlear nerve to the temporal lobe of the brain for interpretation.
So basically that concludes the first part of this lecture. And we will continue here in a moment with part 2.